For our last talk for today, we have Fabien Morel, who will be speaking on equivariant and motivic variations on Smith's theory on action of simple groups.
Thank you very much. So I want to thank the organizer for this invitation. I think my talk is going to be the first talk not dealing with stable homotopy theory in any way. I'm going to stay on the unstable level. I really am going to talk about analogy between equivalent and motivic homotopy theory. So the topic is very classical. I think in the classification of Tom it should be called antiquity rather. So let's start with some recollection on the stuff. So in the 1930, Smith, so yeah, maybe older, yeah. Smith theory deals with cohomological properties of Z mod L CW complexes, finite. So, one example, if you take X finite CW complex with an action of finite Z mod L CW complex, L is a prime, and such that the reduced cohomology, singular cohomology for the moment, is trivial. So reduce is 0, then it implies that the reduced cohomology of the fixed point with model coefficient is 0 as well. Okay, these kind of things. So it was treated by using elementary techniques and the cellular decomposition, of course. Then a little bit later, but still in the antiquity time, so Morel in the 1950s, using his construction, the Morel construction, reformulate this and generalize this a bit. Reformulate this. The so-called Morel construction. So as follows, how does it goes? So with the same assumption on X. So the Morel construction is the following. So we consider a nice contractible Z mod L CW complex with free action. Of Z mod L. Okay, the quotient is well known to be the classifying space. This is what I mean by nice. Then you can form the following construction. So you can cross this space with X, and you can identify both. So this is the construction, and this is the quotient. And this is the Morel construction. Where you identify the action on the left with the action on the right. So sigma yx is equivalent to y sigma x. Okay, it's also a quotient by an action of Z mod L, where you act here on the Euler's way, and here by the inverse action. Okay, so this is called the Morel construction for a general Z mod L space. Now with this assumption, you can apply this also for the fixed points. It's well known, of course, for the most of the people here, so some of the people here that I'm very happy to see after a long time. you get, of course, the action is free. If x here is the action is trivial. If the action is trivial here, it factorizes this Borel construction, the product busy model with x. Okay, so for the fixed point subset, you get this here, and you get a canonical inclusion of this space inside this one. So Borel reformulation is the following. So sorry, this inclusion here induces, so when x is a finite Z model CW complex here, induces an isomorphism on singular mod L cohomology. So it's not finished. When you apply the singular mod L cohomology here, you get a ring homomorphism, an algebra over Z model homomorphism from the cohomology here to this one. But all these spaces are lying over BZ mod L. If you map x to a point, you get a map to BZ mod L. So in fact, in cohomology, this gives you a morphism of the singular cohomology of BZ mod L with quotient Z mod L modules. So after inverting a special element, the class V, so I'm using the module structure of the cohomology here and here over the cohomology of BZ mod L with the model coefficients here, and this is the canonical class. This is the Bochstein of the identity between the class in H1 BZ model Z model, which is the set of morphism from Z model to Z model. So it is related to this result. For instance, you can recover. Why is it a generalization? And well, I will give a word on the proof. So remarks. So it says, so if x is contractible, let me try to recover the first statement here. So it means that the cohomology of x is trivial, but if you look at the definition using the Serre spectral sequence, it implies that the cohomology of this Borel construction here the morphism induced by this projection here, the fiber of trivial homology, so it is an isomorphism, singular homology. So it means that this theorem, it means that the cohomology of the product BZ mod L cross this one after inverting V is the same thing as here. So it means exactly that this tensor product with V inverted here is equal to this algebra with V inverted, which implies, of course, that this ZL algebra has to be ZL, rank 1. Okay, so we prove that the fixed point has trivial cohomology with Z model coefficients. Okay, so we can generalize these. So there were some cases, for instance, if you take the action of Z model on the sphere, the fixed point set is either empty or a sphere. So you can reprove this using this kind of theorem here. Just a remark on the proof. It uses the following remark, which I will use quite a while in the rest. So, second remark. Basically, the proof is to use the cell decomposition and to handle the theorem cell by cell, so to say. Okay, and you have to use something. So, if you look at the cofibration, of Z model CW complex. So with cofiber C, so everything is endowed with a Z model action. Then you apply the Borel construction and you get still. So this is a homotopy Cartesian co-Cartesian square. You still have homotopy co-Cartesian square. Of course, the quotient here is B Z mod L, and this one. So this is also homotopy co-Cartesian. So it means you have Mayavitori's type sequence in singular cohomology and so on, and using induction on the cell decomposition of X, you can prove the theorem, so to say. So the main topic of my talk is to try to adapt this kind of theorems in more algebraic geometry world. First, what about considering an action of Z mod L on a smooth variety and trying to deal with Etale cohomology with Z mod L coefficients. And I will also conclude the talk with an equivalent analog in the motivic case where Z mod L will be replaced by GM, the multiplicative group over K, which I will prove to be a cyclic group of prime order eta. Okay, so I usually say 2, but it's rather eta, so I will come to this. So the main topic is how can one prove this kind of theorem when you don't have any cell decomposition, because in this kind of cases it's really important to use the cell decomposition structure. Some historical remark. I will also conclude with that, hopefully. In the 90s, this is when I was mathematically born. Tom?
Wasn't even ready for it. What can I say?
So Lan, Dwyer, Wilkinson, and some other generalized and gave some generalization of this and more precise. In fact, they prove the following. The cohomology modulo L of the fixed point set is a functor, explicit functor, on what? The cohomology of the borrowed construction as I use the structure as a module over the cohomology, so in fact as an algebra over that cohomology ring here, plus Steenrod square. Steenrod operation, sorry. So it's an explicit functor here, okay, which allows one to reprove everything which was known, and in fact much more. Okay. So in fact this is my aim here. So I will deal with this theorem. So this is proven basically, and I will give some indication that I am optimistic to have such an analog in the motivic case at the end of the talk. So first variation, the Etale one, which is still very much topological. So, but the main problem is that we don't have any cell decomposition. Case. So I will, for simplicity, assume that K is algebraically closed. X is smooth. Variety over K. L is a prime. And well, I just recall that L is always different from the characteristic, which is P. The people who went once at the Orse seminar know that L is always a prime different from P. P is the characteristic, and S, yeah. So what is known is then the fixed point schemes is well defined and is a smooth scheme over K. So everything works fine. So we may ask for the analog of these theorems. So for this we have to know what is the correct notion for the Borel construction. Okay, so problem. What is the Borel construction? And to start with, what is this in this setting? Okay. There are two solutions depending on whether you admit. So I want to deal with Etale cohomology with Z mod L coefficients. Okay. So if you believe that, if you know that this is the Etale cohomology is defined for simplicial smooth schemes, then you can take the simplicial definition for easy mod L, the same one if you want. Okay. So first, usual simplicial set, which you consider as a, so in each dimension it's a finite set of points, and any point you consider as spec of k, which is also a point, and you consider this as a simplicial smooth scheme over k. Okay, and this is very easy. There is no theory, no quotient of a scheme by anything. It's just before taking this quotient, it's a simplicial scheme. In each degree, it's a disjunct union of copies of x, and the action is free, so we just identify some of them, but you get something which is very easy. So simplicial smooth over k. The second one, if you are more geometric, and which was considered by Totaro and Voevodsky, is to use for well, the geometric one version. Take the affine space, so the infinite one, to remove the 0 and to let act mu L of k. But of course, I remember that because k is algebraically closed and L different from the characteristic, mu L of k can be chosen to be isomorphic. It's a cyclic group of order L, so you can choose an isomorphism. Okay, one has to use an isomorphism. It's not perfect. So this is a model, a geometric model for the classifying space here of this. Sorry, this is this one before taking the quotient here. So with the action of mu L is chosen to be identified with the group Z mod L. Okay, and the reason why it's a model is that this is the union of the a n minus 0, and each of them, using the standard computation of Etale cohomology, is cohomologically more and more connected. So the union of all of these has trivial Etale cohomology with Z mod L coefficients. Okay, in the A1 homotopy setting, in fact, this space is A1 contractible. Okay, so this action is very nice here of Z mod L. It's a free action, and in this setting, in fact, the quotient is a smooth variety. Well, for each given n, the quotient by Z mod L is a smooth variety, and the union is an inductive smooth scheme. Okay, so it's a nice model. So one may use both of these construction for the Borel construction, and the theorem all exactly in this way, using both of them. They are equivalent in some sense. So I just want to sketch how to prove this, because of course one of the main problems here, if you have a smooth variety with an action of Z mod L, there is no cell decomposition. You cannot say I will reduce to cells. There is nothing like that. X itself is a cell. So theorem 1, and there will be basically only theorem 2. Okay, so in this talk, so theorem 1, with this assumption, previous assumptions, the morphism I can say morphism of spaces over K. It's a morphism of some objects. So B geometric, or if you take the simplicial one, B Z mod L of simplicial smooth schemes. So this is the product over K. This is an and scheme. This is a smooth scheme mapping to this. Induces, so it's the same theorem. An isomorphism in Etale cohomology with the model quotient after inverting. It's really almost the same because the V is the same. Bochstein of the identity, which is inside H2 Etale of B Z mod L. I said it's the same because, as it is well known, the Etale cohomology of B Z mod L with this definition, the geometric one, Z mod L, or the simplicial one, is canonically isomorphic to the Etale, to the topological one. So it's really almost the same. This is singular cohomology of, and because I am over an algebraically closed field and so on. So the statement is very easy to state. It's the same. So what about the proof without cells? So sketch proof. I will use this fact here, and that a cocartesian square with some nice property will give a cocartesian square, homotopy cocartesian square of borrowed construction. So what do we consider in this case? We have no cell decomposition here. The method was to use the cell decomposition. We don't have this, so the only thing we can use is just the inclusion of, so let's put Y to be the fixed point schemes inside X, so it's a closed immersion, and I consider the complement, omega. It is an open complement. Okay, of this closed immersion. So at some point I have to use, we have to see where to use as L is prime. So the fact that it is prime to the characteristic is already used, but where is it so important? Well, it is not true for L square, for instance, and so on. So it comes instantaneously here. So the action of Z mod L on the complement here, so it's the fact that Z mod L is a cyclic group of prime order. Either the action is free or the action is fixed, so it's a fixed point. So if you remove the fixed point, the action is free. And when you have this, the quotient, so now it's a little bit subtle. I will use here, so well, I didn't, I'm sorry. I should have said it's the same. Well, here, if you use the simplicial version, it's really the same. There is no real quotient. But I want to insist that I will use the geometric one. It is the Etale. Okay. In fact, it's not really true. I could, but I don't want to mess up everything, so and to confuse. You could also use the Zariski or whatever, because you are computing the Etale cohomology. So when you compute the Etale cohomology, you shiftify in some sense. But for the geometric point of view, it's better to say it's the Etale quotient here. Okay, and it's very important because now the quotient here in the category of sheaves in the Etale topology is a smooth scheme because the action is free and of finite dimension. Okay, it's a finite type scheme. Okay, this is very important. Now I apply this property here for this diagram here. So there is another geometric input here. So you have the inclusion. It's an open inclusion here into X. It's equivariant. So I want to collapse these to the points, which is a little bit strange. In topology, to collapse an open subset, it stands to a point, but this is allowed here. And you get something which is X modulo omega. And here I will start using unstable A1 homotopy theory. In the category of space, this is canonically A1 equivalent, and A1 equivalence induces isomorphism in Etale cohomology with the model coefficient because the L is prime to the characteristic, to the Thom space of the normal bundle of the closed immersion here. So this is Y, closed immersion is I here. So it's an inclusion between smooth schemes here, closed immersion. The normal bundle is free, so it's a vector bundle, and it's well known. It's one of the main results of the constructing basic result of A1 homotopy theory is that this relative Thom space of the inclusion is canonically A1 equivalent to the Thom space of the normal bundle. And I claim that this is enough to reprove the theorem here. Okay, so it means you could also prove directly Smith's theorem in topology if you have a differentiable manifold. Okay, you can do the same thing using the purity. It's called the purity theorem. So how does it go? So this implies using this property here, which is also true. It's homotopy co-Cartesian, Cartesian and homotopy Cartesian. So you get the geometric Borel construction here. So it means homotopy co-Cartesian. I will only use it induces long exact Mayer-Vittori type sequence in Etale model cohomology, like for usual covering by two open subsets. Here you get E geometric Z mod L, so Borel construction, and everywhere it's Etale of the Thom space. So I allow myself to replace this by this directly because the Etale cohomology is the same. Well, it's to use a bit, but it's standard. And here it is the geometric classifying space. So it's homotopy co-Cartesian in the sense that this induces a long exact sequence of cohomology groups in the Etale cohomology here. So homotopy co-Cartesian. And that's all. So now everything is on the blackboard here. Well, almost. Of course, I'm a bit hiding some difficulties, but it's relatively elementary. Really elementary. So this induces a long exact sequence of Mayer-Vittori's type in Etale cohomology, and this is a sequence of module of the cohomology, Etale cohomology of this space here, because everybody is defined over this space. Okay, so when I invert the class V, it is still a long exact sequence of Etale cohomology groups. Okay, so this induces. Let me put it this way. Of course, the arrows are the other way around. Etale cohomology, geometric classifying space, the geometric Borel construction X. So I mean this induces Mayer-Vittori's type exact sequence. So it is the classifying space here, Z mod L, and here this is of the Thom space here. So I can invert here V everywhere. Okay, and still a long exact sequence. Yeah. Now comes the geometric input, which is the fundamental one. This one. The action is free, and the quotient is a smooth variety, so finite dimension. So it means that this Borel construction here, the projection to omega modulo Z mod L, which is a smooth variety, is an A1 weak equivalence because the fiber are these A1 contractible spaces. So it's like in topology. Okay, so this is an A1 equivalence, which means this object here is A1 equivalence, so has the same Etale cohomology as a smooth variety, which means finite dimensional. There is only finitely many groups here. So if you invert anything of positive degree, it is 0. And this is exactly the proof. So this is 0 in fact. So if you have such a Mayer-Vittorix type blah 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 with 1 which is 0, it's just a direct sum decomposition. So this is a direct sum of this and this. Okay? So it's a direct sum here. I think I will remove the coefficient Z model. It's from now on it's always Z model as coefficient plus and it's an isomorphic as a module or that ring with V inverted, so direct sum Etale cohomology of this one, Borel construction of X. So this is what we want to understand with V inverted. Now this trick allows one to, so you can take 1 minute, I'm not joking, to say now it is sufficient to prove the theorem in the case where instead of the inclusion of the fixed point in X, you look at the inclusion of the fixed point in the normal bundle. It's a classical trick in algebraic geometry using the deformation to the normal bundle of purity, because what we want to prove at the end is that this object should be the same thing as the cohomology of this classifying space with V inverted tensor the cohomology of the fixed point. So it means that we have to prove that this one, which now doesn't depend on X at all here because it's a Thom space, should be isomorphic to the cohomology of the fixed point set tensor this cohomology of BZ mod L with V inverted plus a constant term, which means it has nothing to do, what we have to prove has nothing to do anymore with X. And so we reduce to prove that this direct sum is nothing but so I rephrase what I said, V minus 1 plus Etale cohomology of the B Z mod L tensor the fixed point cohomology of the fixed point. I'm sorry, I'm writing this very small, so here's V minus 1, V is inverted everywhere. We have to prove exactly this isomorphism here now, okay, that this is isomorphic to this one. But this has nothing to do with X anymore. Okay, now to input, and it's sufficient. Of course, you have to check that this isomorphism is compatible with the map from X to the fixed point. Okay, but it's clear. So, what is the last remark? The last remark is that it behaves like if the fixed point set, so Y, is the fixed point of the action of Z mod L on the normal bundle. It's not exactly true, but one can reduce to this case. Now, so we have Y, the fixed point set. We have the inclusion, the zero section of the normal bundle. So nu I is a normal bundle, so it's a bundle over Y here. And so there is an action of Z mod L here, of course. Okay, and you have this fixed point set of this action here, Z. Everything's closed. And the fact is that this inclusion here is an A1 weak equivalence. It's not true in general that it's the same thing, but locally, so now I go a little bit quicker. Locally, so the fact that L is prime to the characteristic, to the base field, if you have an action, a linear action, of course it's a linear action of Z mod L on this vector bundle. So if you fix a fiber, a point here on the base field, the action of Z mod L on each of the fiber, vector bundle, is a linear, it's semi-simple. So it decomposes canonically as a direct sum considering the eigenvalues, which are all in the base field because K is algebraically closed. So there is a canonical decomposition. It means locally this vector bundle split canonically. And the action, okay, is fixed the subvector space of the eigenvalue 0, of course, 1, sorry, it's fixed. And the other one, the fixed points, are not, so the action is free, and the fixed point is just a 0 vector space. So it's easy to check that in fact locally the fixed point scheme of this is a subvector space, so fiber by fiber, which means it is the inclusion is an equivalence here. Okay, so this is an A1 equivalence here. Okay, so now it's easy to compute. I want to this term, the Borel construction of the normal of the Thom space of the normal bundle here is very easy to compute. It's easy to check that because it means that this is the same thing as y, okay, and the other one. So it's easy to check that this implies the result. I think I want to go a bit quickly. So just using the facts I put on the blackboard, it's easy to conclude. Okay, formally, implies the result. Okay, so in some sense, very shortly said, so it's not true. If you assume that the fixed point set of this action is y, it means this deformation to the normal bundle allows one, and this isomorphism here allows one to reduce to the case of this inclusion here, where the fixed point is the zero section, which is easy to check. This is very easy to check. Okay, it's almost true. Okay, using this trick here. So a remark. There is also another approach to this. It is a joint work with Olivier Authion, and it uses a remark of Serre, work of Serre, some time ago, so maybe 10 years ago, 15 years ago, proving, and it's more general, so using sheaf theory, sheaf in the Etale topology, but using basically nothing. And we were surprised, and we try. In fact, it seems that it's possible also to reprove this in more general case, for instance, that you don't have to assume that X is smooth. You take a finite type scheme over K with an action of Z mod L. Serre proved that if the Etale cohomology of X Z mod L is trivial, in fact, he proved if the Etale cohomology is trivial up from a certain dimension here, you give a specific bound where the Etale cohomology of the fixed point scheme, which is whatever singular, is also zero. Then, so it means radius here, then it is also true here. And in fact, so it was very striking. So in fact, we look at that carefully, and it seems to be possible to realize this in the without assuming this, but reformulating this in terms of a Borel construction as well. Okay. So it's another way, I will not say anything there, to prove this kind of theorem without cell decomposition, okay, directly using sheaves. So now I come to another remark on that, which is also a first motivic variation. I will change the cohomology theory. You might ask, for instance, what happens if we use mod L motivic cohomology instead of Etale cohomology? Okay, is it true or not? So what is true? So it's the first one, but it changes the cohomology but not the group. And the last part of the talk, I will change everything. I will take a motivic cohomology and I will change the group. So second remark. So, motivic variation 1. I like this analogy with music, variation 1, 2. One may state an analog. There are several analogues, of course. A lot of variation. I put an S, variations on, so because you can imagine a lot of other result close to result using. So I'm an old-fashioned guy, so I will use the notation for motivic cohomology that Voyevsky used in the first preprint, which are not even available anywhere. Okay, it was mu. Then it became Beilinson or well, but the first preprint was this. So motivic cohomology. It's bigraded with the mod L coefficient. Okay. Still being on algebraically closed field, but in fact you can also remove this assumption and say something. And I also remove the fact that I take the quotient in the Etale topology and the naive simply short construction. Of course, some people here have some name, I will not say this, will cry because it uses a very hard theorem, but it's very analog. Okay, so it's the same statement, but not after inverting one element, but two. You can always say, but if you invert two elements, you can take the product and you can invert only this one. Okay, but there are some results of Dwyer-Wilkinson inverting several elements, so 10 classes of representation of the group involved and so on and so on. So what is the point? So the same statement, I will not, okay, so same statement, I will not write it here. I want to be cool at the end. Same statement. So you take the fixed point scheme, it's smooth scheme, X is smooth, so okay. But you use motivic cohomology with the model coefficient, and this canonical morphism induces an isomorphism after inverting two elements. So V, the same V, which in fact happens to lead already in motivic cohomology, H2 of BGM Z mod L ZL of 1. It was an element considered by Vojevodsky. So Vojevodsky computed entirely the mod L motivic cohomology of that geometric classifying space, which is okay. And so it is the Bockstein of rho. You saw rho several times here. And of course, so these elements are defined, so I don't need to define them, tau. Because by a non-trivial result of Vojevodsky, using tau or for L equal 2, and generator, so sigma for L different from 2. Okay? Because by result of Vojevodsky, if you invert tau for L equal 2 or this generator here, in the model motivic cohomology, you get model Etale cohomology. So then you can complain, oh, it's not a true analog, but it looks like an analog. Okay? Because if you invert this one, then in fact you get model Etale cohomology. Okay? And if you invert the other one, you get the previous theorem. Okay? So I'm working on understanding maybe a better proof of this. Okay? But there is also an analog of this. So there are something which are true also using this and not using Etale quotient and so on. So now I'm coming to the motivic variation 2, where I'm going to change. Well, there will be no L. Well, there will be L. L will be eta. Okay. So in fact, I will deal with motivic cohomology with integral coefficients. Okay. And the group will be GM. So I have to convince you that G is some kind of cyclic group of prime order. First. I don't have time also. There is an analog in the Etale setting of computing the Etale cohomology of the fixed point as a functor blah blah blah, which is not completely trivial. It looks like trivial because oh yeah, it's already done. Not exactly, because you could say you use the Etale realization functor, but there is no way to prove that the Etale homotopy type of the fixed point has something to do with a fixed point of the Etale realization or whatever. So there is a kind of subtlety anyway. Okay, but you can compute also, of course, using the T or fixed functor, whatever, the Etale cohomology of the fixed point in this setting. Okay, but I don't have time. I will mention this at the end of the talk in another context. So I had 4 pages, and I have a quarter, and I have only 1 page, so it's perfect. So last part, so motivic variation 2. which is something that I had in mind for a long time, of course. As I explained to Tom, although he's fighting against that, you are always, disturbed the whole life long by your advisor. Okay, what is told you in the PhD time, you cannot get out. Okay, so you may call this antiquity or whatever, but it's so first, Etale cohomology with the model quotient. There is no L, will become, in fact, motivic cohomology with Z coefficients. In fact, so, well, I will give some remark at the end. And Z mod L, in fact, will become GM. Okay, so we consider GM action on smooth schemes over K. And K is any field. Well, first, so claim or idea cyclic group of order eta, which is prime. So what does it mean? I usually say of order 2. Well, because so in some sense you have to think about GM. So you have to think in all this intuition stuff. In fact, contrary to the first intuition, the correct intuition is related to the real topology. Although he will complain again, probably. I mean, this gives you. So, for instance, GM from the real point of view is S0, 2 points. Okay, and in fact, it is a discrete object. Cohomologically trivial, there is no cohomology in this world. GM has no cohomology. So it's really discrete in degree 0. It's not of degree 1, 1, it's of degree 0, nothing. Okay? And the homotopy type of the real point is in topology plus or minus 1. So it is really S0. Okay? The second one, of course, you can say, well, GM of the complex is S1 and so on. And of course, what I'm going to say, for the one who knows this, is very much inspired by, again, it's a family story, by the work of Jean Lannes and François-Xavier Don on the S1 analog of the work of Lannes on Z mod P, of course. It's hidden, so it's in some sense the both at the same time. So this is the dream. But still, so another argument is the following. GM is min or K theory in degree 1. So it's a quotient of the free strictly A1 even sheaf on 1. So GM is a sphere. Okay, so it's a pointed sphere, so it's a twisted version of S0 in some sense. Okay, you have 2 points but twisted. You take the free strictly, so the free discrete sheaf on that twisted version of S0. Okay, it's a quotient. This is K1 min of it. And it's a quotient by the free sheaf on 2 units. Okay, so GM smash 2, it's also a twisted sphere of weight 2. So it's also a sphere, some sort of degree, dimension 0 sphere. And the morphism here is eta. So this is just a formula that K1 minor is a quotient of K1 minor of it by eta. But it says that this is a free group on 1 symbol, it's a free group on 2 symbol, and this is a co-kernel. So it's a cyclic group of order eta. Okay. I have also some other stuff to buy, but not to sell, sorry, but I don't have the time to prove it. I like it. So yeah, in the A1 sense, let's say very quickly, you can take the amalgamation of GM and GM in the A1 sense. So it's now a non-commutative, strongly A1 sheaf of groups. So it's the analog of the sum of copy of GM and GM in this world. So you should think about Z mod 2 amalgamated with Z mod 2. Okay? Then you take the morphism to the product GM cross GM. So Z mod 2 amalgamated with Z mod 2 mapping to the product Z mod 2 and Z mod 2. The kernel is cyclic of rank 1. And in fact, it's a characterization of Z mod 2, which I like. It's the only discrete group which is non-trivial. So I mean the kernel is non-trivial, and if you take the amalgamation of G and G, mapping to G cross G, the kernel is abelian. For all the other groups, it's non-abelian. In fact, it's well known that the kernel here, well, okay, I will not prove it, okay? So the kernel here in that case is K2 minor V. So it's a cyclic group, commutative. Rank 1, so on 2, symbol of order 2 here, okay? Yeah. It's analog of the following fibration, P infinity, wedge P infinity, mapping to P infinity cross P infinity, and the fiber is A2 minus 0. You can prove that there is such a fibration, okay? And this proves this. So, and it's also proof that this is Z mod 2, okay? So, now, I will not use this, of course. Well, you use this kind of thing, of course. It's hidden. So now I claim that once you agree with this, then there is theorem 2, which is exactly the same. So in fact, I'm already done. Okay? I just put the same statement. Well, with a little. So let X be a smooth scheme with an action of GM, but with an essential action of GM. I will explain what it means. So without this assumption, with an action of GM, it is known that independent, the fixed point scheme is always smooth. So it's also another proof that GM is a cyclic group, okay, because it's a theorem which is always true. Well, so what I'm going to use, I can be serious a bit, is that the linear representation of GM, like the one of ZL in classic prime 2L, are semi-simple. Okay, it's a very important fact, plus some geometric stuff. So this is smooth, so you can state the same theorem. Okay, so known, yeah. And second fact, well, I always well ask myself what should be the analog of well, Sullivan conjecture and so on. Yeah, what is the homotopy fixed point? And you heard probably some talk here that there are two choices. For GM, everything is solved because there is only one choice. You don't have to worry about that. So there is only one meaning on that. Because the quotient in the Etale, in Zariski, in this topology by GM is the same. Okay? So it's uniquely defined. Which is good. So the same in Zariski. So all the ingredients are there. Misnevich or Etale. If not, for instance, if you look at other cases, it will be then it's a bit messy. Okay, you have to care. Okay, I told you have to take. You can take the ZL quotient in the Zariski topology, but then you have to care which cohomology theory you use and what do you inverse and so on. Here there is nothing, and it works just exactly the same way. So then the inclusion BGM or P infinity, it's the same thing, cross the fixed point scheme here so let me call this way. One geometric model of EGM is A infinity minus 0, the same one, with the action of GM, which is free by homotopy on that. Yeah, so it's a nice definition here. This induces an isomorphism on integral motivic cohomology after you invert the class, the same class, the C1, which is a Chen class of the line bundle of BGM in H21 of the motivic cohomology of BGM. So is an isomorphism, induces an isomorphism. Motivic cohomology after inverting C1 in H2 BGM of Z1. And it's the same formula. It's also the Chen classes of the canonical line of BGM, the universal one. The proof is the same. So I still have 5 minutes, but I will only do remark. The proof is the same. Use the purity theorem. Proof? Same. Well, I have to say what is an essential action. I will explain it in 1 second, because the proof is the same. You put the same diagram. Essential is the fact that GM is not exactly like a usual cyclic group of prime order. Means that GM acts freely on the complement here of the fixed point here, which is automatic in the case of usual one. But what can happen, and the only case, so it is equivalent to the fact that one cannot induce the action of GM on X from a quotient, a non-trivial quotient of GM. There are a lot of quotient of GM in the geometric setting. Okay, so if you take the map which raise z to the power n, where n is prime to the characteristic, this is a quotient in the Etale topology. It's a quotient scheme. GM modulo mu n is GM. Okay. So you have to consider an action of GM on a scheme, smooth scheme here, which cannot be factorized by the smaller quotient. And it's equivalent to say that it's generically on the generic point free, okay? Which means on this open subset it's free, in fact. Okay. So it's not a big assumption. But once you have this, then the same diagram and the same proof works, because this is A1 equivalent to omega modulo GM, which now is a smooth variety of finite dimension, and so you get the same proof using Thom space of nu I, where nu I is, so I is the inclusion here, and here's BGM. So it's the same proof except one thing. It's not true that the motivic homology with integral quotient is finite of a smooth scheme. But the class we are considering here is this bidegree, is a pure bidegree, 2, 1. So all the power are in 4, 2 or 2n, n. And what is true is that in bidegree 2n, n, a smooth variety, the cohomology will vanish eventually. So if you invert a power, it would be 0. Okay. Okay. So it's still the same thing, same truth. So now 2 minutes. And so what? I have a list of open problems. First, the motivic homology of the fixed point should be a functor in some cases, of course. I have some precise idea, but the proof should be, so there are 2 problems, to find the functors and to find the proof. I have an idea on the proof, but not yet completely on the functor. So what about the T functor theory in this setting? Functor of motivic homology of the borrowed construction. Of course, there will be some assumption. For instance, that the motivic homology of X is free, that X is, for instance, a projective space, but it's a free module of the cohomology, motivic homology of the points, things like that. That it's, the motive is decomposed as a sum of Tate's motives, something like that. There is a need for a flatness assumption on all the cohomology involved here. Okay, so that should be okay. But I mentioned something that here the motivic homology is with Z coefficient, and I didn't say that really. I told you that GM is an analog of Z mod 2 twisted, And in some sense, although it doesn't seem like that, the motivic cohomology with integral coefficient is also an analog of singular, so homology or cohomology with Z02 coefficient. So there should be some operation, like squaring operation, which are hidden, which are integral, which for the one who knows the definition of the T functor and so on, which should allow to define this functor. So what are the stable operations to be considered in this setting and so on. So I have some idea on that, okay? The proof, so after you know the functor, should use, I will only write the name, I will not have time to say this. There is a nice theorem of Birula, saying that if you have an action of GM on a smooth projective scheme, there is an incredibly simple decomposition, stratification of the scheme, such that if you take the strats, these are A1 equivalent to one connected component of the fixed point scheme. So there is a very explicit connection, geometric connection, between X and the fixed point here. So I guess if you have the correct functor, the proof that it's an isomorphism should be easy. Now here's another generalization. So this is completely now in the last minute. The motive. So this is just motivic cohomology, which is not satisfying. The motive, which is something else, of the fixed point. So of course, should be a functor of, I don't know what, motive of the Borel construction. As what? I don't know. Some structure, but it's, I mean, much deeper. Here, these are graded group. This is a motive, okay? So under some assumption on X, the motive of the fixed point scheme should be an explicit functor, should only depend on this, plus a structure, and so on and so on. And of course, let me mention this. This is my family stuff. The completion of the fixed point set here should be the homotopy fixed point set of the completion of X. Here the problem is to define what completion. So what is amazing is it should be the integral completion using Bousfield-Kine process for the adjunction with motives. So it means integral motives. It's the analog of the integral completion, but motivically complete. What is amazing, okay, so of course it's not proven, if K has finite cohomological dimension in the Etale topology, I think the completion could be removed. In fact, any smooth variety, so this is for smooth variety, a smooth variety should be, all of them which I know should be in fact already complete. So in fact, it should give an expression of the fixed point scheme as a functor on the X itself. Okay, so thank you very much.
So you said that motivic cohomology with Z coefficients is analogous to singular with Z mod 2?
Yeah, I did.
Can you say a little bit more about that?
Because you didn't complain when I said that GM is an analog of Z mod 2. So, well, so motivic cohomology with integral coefficient is the analog of the, well, motivic cohomology is not the true motivic cohomology. Tom mentioned this. If you look at this, all this effective stuff and this structure, there is an integral version, which is, I don't know how it is noted nowadays. What is the classical notation? So there is an analog of the, well, I don't know. Sorry? Well, let's denote it HA1. Okay. Okay. So this, in this theory, so it's a bigraded theory. It's really like the, in the sense of Quillen, it's the homology or cohomology theory obtained by abelianization of spaces. So you have to take the Dirac category of sheaves and you A1 localize. That's it, nothing else. Okay. In that theory, eta is non-zero. So, and there is something like a formula that if you mod out eta in this definition, you get integral motivic cohomology. Well, I know it's not true, but this is the basic idea. So the category of motive dm is some kind of quotient of a more finer Dirac category by eta. So if you believe that eta is some kind of form of 2, it means that this is, that the motivic homology with integral coefficient is a kind of, it's a twisted version of something like singular, but it behaves in the same way. Well, motivic homology through a real embedding maps to singular motivic, singular homology modulo 2. You cannot lift to Z. So it's the same idea. So motivic homology with integral coefficient is compatible with the mod 2 singular homology through the real points. So it's also another remark.
I'm a little confused about your point 2. I mean, I know it's a conjecture, but is there actually an analog in ordinary topology of that?
Yeah, because of course.
You could say everything is formal, but
I mean, there is an analog with mod 2 or with mod L, because the cohomology is known. But in usual topology, the cohomology is the same as homology, up to very little, and the homology modulo L is the same thing as the motive modulo L, because it's just a chain complex.
Right, but I guess I'm asking: is there like a chain complex construction of Land's T functor, or are you just
no, of course not. There is no Z analog. Well, but there is a Land theorem using S1 actions. So, for instance, the theorem of Land computing BZ mod L maps from BZ mod L to X under some assumption is also true for S1, for some assumption X. So I claim that should be. So there should be, for instance, a computation. So the people doing some, there should be also an analog of computing map from BGM to BG, for instance, or to X with some assumption on X, but for BG, G a split group, it should be true. Okay, because this flatness assumption should be there and so on. So there should be an analog,
But still, it's a functor in the homology or cohomology, right? So I mean,
it's not clear right now. So of course, so here there is a hope because it's cohomology and it should be a very explicit definition. It should be a subgroup. In the case of mod 2 model homology, the functor was simplified by Dwyer-Wilkerson. If you take the cohomology of the Borel construction, you invert V and you take the submodule, which is the how do you say this? Unstabilization. Okay, so it's a model of the singular algebra, but not unstable. So you take the biggest, so this is a functor. So I think there is a way to define this not yet completely defined functor, but there is an analog. Okay. In the case of motive, of course, it's completely open because it's not free. So if you assume it's a direct sum of Tate motive, maybe you can define, but it will be complicated. Okay, it's not so. There will be derived stuff behind. But I think there should be some analog with some assumption on X of this type. Okay. It should be true for any projective space and product of projective space and something like that. With any action of GM.
Oh, okay. I have maybe a naive question or something. Going back to the original Smith theory, and there's this, fun thing that Z mod 6 acts on Euclidean, high enough Euclidean space counterfloyd example with no fixed points. Is there?
I never thought because in the you mean in the case of 6 or in the case of GM?
Well, 6 is not a prime, right?
Yeah. Okay. No, but I mean, okay. So you mean not in the analogy with GM? So because GM there is no
space or something without fixed point.
I don't know. Maybe I don't know. No idea. I never thought. So maybe one has to check whether this example is a bit algebraic. If the action is algebraic, if you can make it into an action of affine space, or I don't know, something contractible. Okay. So I don't know. Never thought about that.
How many of these cohomology operations do you
I mean, you can try to extend the squaring. This is the only one. So I think there is a possibility to have an explicit list of defining the functor here, for instance, here. Here, of course, not. I don't know. I mean, it should be really. But here, I think there is some way because theoretically, the integral motivic homology of any Alma-MacLane space is known of integral. So you should. So I think I'm very positive on that. Okay.
And is there a notion of instability, like what?
There should be a notion. It's a work in progress. Okay, so it's very. So there is a part which is completely known and so on, and this is so. But I'm very optimistic. Yeah.
I just thought I'd point out that alternative approach using sheaves is in a paper of mine.
This other approach using sheaves for GM, no.
No, not for GM.
For the other one. Well, it's just the fact that you.
No, I said it's in a paper of mine from about 15 years ago.
Oh, okay, I'm sorry. It was.
fine, I just
Do you
thought
mean it's
that's what you
before?
said.
Okay, it's before Serre. Because I think Serre is also around 15 years ago. So if Serre didn't cite you, or so I'm sorry. Okay. Then you should write me an email, and with a reference. I would be interested. Yeah. I looked at all the books with sheaves and equivalent homotopy theory, and I didn't. So, please.
No, I mean, yeah, it's really based on the results of Jeremy Rickard from.
Okay. Okay. Didn't know.
A nice property of cyclic groups is that if you quotient by a subgroup, you still get a cyclic group, and you have these nice quotients.
But I'm trying to deal with cyclic prime, so there is no such.
So the GM over GM squared.
Yeah, but it's I know, but it's not a subgroup. It's an overgroup. This is not a subgroup. It's but it's in the sense of in the sense of cotonic covering. Yeah, it's not.
Well,
Of course, there is no analogy. I mean,
Is there
yeah.
a way to view GM over GM squared as some kind of cyclic group?
I think we had this discussion already. No? Maybe in my office and yeah. So okay. I still don't know.